I'm very glad you're joining my online presentation. As you can see, we're talking about big numbers and big troubles. More specifically, we're analyzing ECTSA implementations for a very serious threat that could break those schemes, namely nonce leakage. It's a form of a side channel. ECTSA is amongst the most widely used signature schemes today. So we can safely assert they are also the most analyzed ones. Can we? How secure are ECTSA implementations? And specifically, how do they prevent side channels? When we started analyzing it, we felt like searching for a needle in a haystack, not knowing whether any needles are left to find. We started off analyzing the popular OpenSSL library, and then also included LibreSSL and BoringSSL. Our analysis was a continuous jumping around between manual code review and automation. And in particular, we were using a special method called differential address trace analysis, DATA, which I presented at USENIX 2018. And we used this approach, DATA, and extended it. We added new leakage models which were dedicated and designed for finding nonce leakage. And we also developed a new graphical user interface, which greatly helped us find stuff we couldn't find before. But long story short, it took a great amount of effort to actually discover the first vulnerability. But once we found it, a whole field opened up for us. Suddenly we knew what to search for. And unluckily, we were quite successful. So let's step back and look at what ECTSA signatures are. We always have some form of document or data structure which we want to sign with a signature key shown in yellow here. And out comes a signature, a digital signature. And ECTSA signature schemes always involve a so-called nonce, a number only used once. It needs to be secret, very important. As soon as we know a few bits of the nonce, we can mount a key recovery attack and retrieve the yellow key. We start off with Nonce Generation, and the nonces are denoted as K in this presentation. The next steps for ECTSA are Exponentiation, Inversion, and the final multiplication step. What we did is we analyzed all of those steps with our data tool. And surprisingly, we found nonce leakage not only in the generation of nonces, but also in the exponentiation, in the inversion, and in the final multiplication. So essentially in all computation steps. And if you combine leakage which you found, you can mount a key recovery attack and break the signatures and retrieve the yellow key at the top. So let's briefly go through the steps and see what we found. We start off with nonce generation. Here you can see a nonce K1, which has some representation in hexadecimal here. But OpenSSL needs to break down this representation in so-called big numbers. And it does so by splitting the number into so-called limbs. So we have 3 limbs. When OpenSSL does computations, for example an addition, it first accesses the first limb, then the second limb, and then the last limb. However, if we now use a slightly different nonce, K2, which is just a bit smaller, we see that it only fills up 2 limbs, and the topmost limb stays empty. So if OpenSSL now computes on K2, it will already abort after the second limb. The third limb is not accessed. So this creates a form of a side channel leakage. By counting the number of iterations, we can learn the 0 limb of K2 here. And this can easily be done, this counting of iterations, for example with a flush and reload attack. One just needs to probe the right function which is used. And for key recovery, a simple lattice attack should suffice. To give you an example, the popular P521 curve leaks 9 bits every 512th signature. And this is fairly enough to mount a lattice attack and recover the key. So, to step back, what did we see here? As soon as a nonce is slightly above a word boundary, we might be unlucky and have this sort of leakage. And we found this nonce generation leakage, these small nonces, leaking all over the libraries. Let's go on to the next one, exponentiation. And actually, exponentiation is one of the most important steps. and also one of the most analyzed ones. But still we found in total 6 distinct vulnerabilities, which mostly have to do with a certain scheme called nonce padding. And nonce padding itself is meant as a side channel defense to prevent this kind of leakage, but we found itself to be leaky. It was awarded with 2 CVEs, by the way, and we also showed a full key recovery attack in practice in an SGX setting. Now let's have a look at how nonce padding works. We have this modulus Q and the nonce K, which needs to be padded. And we do padding by simply adding K plus Q and doing this another time. If we now have a slightly different nonce, we also do this addition. And now after 1 addition to the left and after 2 additions from the right, we can see that our padded nonces have the same bit length. These nonces, these padded nonces, are input into the exponentiation algorithm. If we wouldn't do this, if we only input the unpadded nonce into the exponentiation, then the exponentiation step would leak via a side channel. That's why we have this padding in place. But wait, isn't padding itself already leaking? On the right hand side we have 2 additions, on the left hand side we have 1 addition. Actually this would be a side channel, but OpenSSL took care of it and also performs a dummy addition on the left hand side. But what we found out with our tool is that on the right hand side we have 1 resize operation, whereas on the left hand side we have 2 resize operations happening during the addition in the low-level routines. So again, the number of resize operations leak the topmost 0 bits. They are shown in red here. And again, as before, this side channel is quite easy to exploit. We just need to probe to attack the resize function. And the resize has a deep call stack calling down into the libc with malloc and all this stuff. So you have quite an amount of functions which you can choose from to attack. And in the end, you can again mount a lattice key recovery attack. And this nonce padding issue always happens when the modulus Q is slightly below, not above, but below a word boundary. In this example, you see the 2 FFs have 8 topmost bits set. So in total, in this example, we can leak 8 bits of the nonce. To go on, we have a brief look also at the inversion step here. The details are not so important, but you just see here that the nonce K shown in green at the top is somehow inverted. While we already found a leaky division step here in this first iteration of this while loop in line 3, I'm gonna talk about this sign operation here. And this sign variable keeps track of the sign bit of the outcome of the inverse nonce. And in the end, if the sign bit is negative, we do this final negation step. And we found this negation step to be leaky. We inverted many random nonces and plotted them here as a histogram. And one can see that some nonces have a smaller bit length, while others have a higher bit length, shown on the x-axis. If we now include those nonces where a negation step happens, one can see a clear bias. Namely that whenever the topmost bit of the inverse nonce is 1, we know that the negation step must have happened. And whenever no negation happened, we know that the topmost bit is 0. This is a perfect side channel. So, by probing with, for example, a flush and reload attack, this negation step, we can leak the topmost bit of the inverse nonce. And this also applies to other parameter sets. For example, 224 bits or 256 bits. And in this case, we cannot mount a lattice attack, but a so-called Bleichenbacher attack, since we only leak very few bits, 1 bit in this case. So I will conclude with a short demonstration of our tool, of our GUI, such that you know what you can use later on for your own analysis. Here you can see the data tool, the GUI, showing the results for BoringSSL. Actually, we also found a tiny leak in BoringSSL. Here you can see the call stack. We found some leaky addition here, which luckily is not critical because we are only dealing with the private key loading here, which is only happening once. But if we go down a bit, we can see that there is some leak happening here in this Montgomery addition, which is done during the Montgomery multiplication in ECDSA. We can click, and on the right hand side you see the exact function where the leak happens. There's some leaky if condition here, which depending on these variables xnag, ynag, has some conditional code execution. If we have a look at the assembler code here, you see this jump compare structure here. And actually for some cases, namely when the window of the nonce is all 0, we have a different jump pattern here, which we could exploit, for example, with a very special SGX attack, which will also be presented at this USENIX conference. Let's sum up. What are the key insights of this work? First, we should never assume that prominent software is just secure because many people have had a look at it. In fact, we found 10 Nonce leakage vulnerabilities, many of which were unknown previously. We found them in all essential computation steps of ECDSA. For Open and LibreSSL, we found that they have serious issues with big numbers, and whenever a big number is close to a word boundary, slightly above or slightly below, a leakage may happen. Luckily, BoringSSL did a better job here. We only found a tiny leak in this point addition, which I showed you before. And if you're interested whether such a tiny leak can be exploited in practice, you should have a look at this copycat talk at USENIX this year. Finally, automated tools like data were an essential step for us to find many of those vulnerabilities. But here's a warning, you need to know what you're looking for. Otherwise, you're really searching for a needle in a haystack. Thanks for listening.